Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're continuing our examination of amines, and we're continuing with a look into the preparation of amines. In the last scribblecast lecture, we examined the Gabriel phthalimide synthesis, a very important synthesis for unsubstituted amines and a synthesis for alpha amino acids. Well, we're going to continue by looking at other preparations of amines. One of the other preparations is the reduction of aromatic nitro compounds. That is, you can take an aromatic ring that has a nitro group on it and react it so as to reduce the nitro group. Now, it is a two-step process, and we will examine why it's two steps. Now, we can use iron HCl, or equally, you could use tin HCl. Now, what's interesting is the iron or the tin will reduce, in conjunction with the HCl, will reduce the oxygen groups down to an NH2, and you'll get an aniline. However, because the reagent is an acid, the aniline will be protonated. So you will have NH3 positive, the anilinium ion. And so often we hit it in a second step with H2O and base to isolate aniline. So overall, the reaction is a two-step process where one, we have either iron HCl or tin HCl. I'll use iron HCl, followed by H2O and hydroxide. Remember, the 1 and the 2 mean two separate processes. First, you do the iron HCl reaction, followed by H2O and base. Well, we have several reduction reactions. Aromatic nitro compounds are not the only compounds that can be reduced. We've also previously learned that aromatic cyano compounds, such as benzonitrile, can be reduced. Since it is a carboxylic acid derivative, you use lithium aluminum hydride, the more powerful metal hydride. Lithium aluminum hydride, then in a subsequent step, add water, and you will convert your benzonitrile into a benzyl amine. We have also seen the reduction of amides. If we take an amide, another carboxylic acid derivative, and it may be substituted or unsubstituted, it does not matter. Let's use a substituted one. So NN-diethyl propanamide. I use the exact same reagent as I did in the nitrile case. Lithium aluminum hydride, and H2O. And essentially what happens is the C double bond O, the double bond O disappears and it becomes a CH2. We end up with NN diethyl 1-propanamine. So NN diethyl 1-propanamine. All right. And of course, there is reductive amination of aldehydes and ketones. It's a two-step process that involves conversion of the aldehyde or ketone to an imine first. So for example, we could take ethylamine and of course we have to react that at pH 4 to 5. So I better extend my arrow. And then step 2, we use nickel, hydrogen, heat, pressure as necessary. And essentially you go through the imine first. So step 1 will produce a double bond N, and off of that N will be a CH2, CH3. And the net result of this, of course, CH3, your C double bond N gets hydrogenated. You produce an NH, CH2, CH3. Okay. So N-ethyl propan-2-amine is produced. So imines can be reduced. And so amines are produced by a series of reduction processes. All right. There's a new reaction. All of these reactions that we've seen as reduction have pretty much been reviewed. Reduction of aromatic nitro compounds, we covered last semester in aromaticity. Nitrile and amide reduction, we just finished in the carboxylic acid derivative section. And reductive amination of the ketone, well, that was done in aldehydes and ketones. We do have a new reaction to look at, which is a preparation of an amine. It's a very interesting reaction, and it is the synthesis by rearrangement of an unsubstituted amide. All right. And in this case, the reaction or reacting amide must be unsubstituted. That is, off of the nitrogen, there can only be hydrogens. So suppose I have a unsubstituted amide. such as this. Okay, butanamide. If I react this molecule with Br2 in the presence of 4 equivalents of base, 4 equivalents of base, I will produce as my product propanamine, carbonate anion, two waters, and 2 bromide anions. Now, this reaction is very interesting because it shows the loss of a carbon. The initial amide is a 4-carbon chain. The resultant amine only has 3 carbons. The CO seems to be removed from the molecule to form the carbonate dianion. In order to understand this, we must take a look at the mechanism of the rearrangement. Look at the mechanism of the overall reaction. So let's begin, and let's start with step 1. Step 1, and that's going to be deprotonation followed by bromination. Deprotonation, bromination. So the amide remember, amides are not basic because the lone pair on the nitrogen is resonance stabilized. As a result, however, they are weakly acidic, so that base can come in. So base can come in, grab a proton and go off as water, and you get the deprotonated amide. Effectively, the nitrogen has 2 lone pairs and a minus. Now, this, you should note, is resonance stabilized, this anion. This contributes to the ability of the base hydroxide to deprotonate the nitrogen. I can dump a lone pair in here. Move those electrons out. Okay, so there's resonance stabilization of the resultant anion, and that facilitates the base to deprotonate. What's next is that Br2 comes in and it's attacked by the anion. The anion kicks up bromide. The Br2 bond is extremely polarizable. As it approaches the negative charge, it polarizes, and a Br plus, delta plus forms, and the N minus breaks the bromine-bromine bond. The result, of course, I'll let R be my propyl group, is C double bond O, N, H, lone pair, and you have a bromine now attached to this. You also get off Br minus. Okay. Now step 2 is deprotonation of this brominated amide. All right. So we can make some room here. I'll put the plus bromide up here. So there's one of the bromides that is formed. And I'm going to just so here is the C double bond O. And H, Br. Once again, base comes in, OH, minus, and H2O. We deprotonate the hydrogen off the amide a second time. In this case, not only is the anion that results resonance stabilized, but the bromine being electronegative helps stabilize it. And so while the negative charge formation seems to be fairly stable, or should be, the molecule overall is unstable because of its ability to rearrange. And the rearrangement that occurs is not unlike a 1,2 alkyl shift. We'll call this step 3. Step 3 is rearrangement. And the rearrangement is such that it forms a molecule called an isocyanate. So let's take a look at this shift, if you like. So what we have here is our CH3CH2. We have a C double bond O. We have an N, which has 2 lone pairs, and we have a Br. Overall, what happens is the propyl does 1,2 shift towards nitrogen. A lone pair dumps in towards the C double bond O to make a pi bond, and the 2 electrons of the nitrogen bromine bond move towards bromine, and the bromine goes off as a Br minus. If you like, we could draw a transition state for this. And let's just put in the bond forming and bond breaking, if you like. So we're going to have a C and an N here. It's a bond. A double bond O. Okay, and let's use black for bond forming. So there is a bond forming from carbon to the nitrogen. There's also a new bond forming, if you like, from this nitrogen to the carbon. Okay, so I could write bond forming. Bond forming is black. Okay. And let's use red for bond breaking. And there is, if you like, a delta minus. The negative charge is leaving the nitrogen, because remember there's a full negative on the bromine, and it's transferring a full negative on the nitrogen, and the negative charge is leaving nitrogen and transferring to the bromine. So there's two delta minuses here once you're halfway, and that transfer is only halfway. Okay, so let's get red again and go bond breaking. So we got bond breaking here and a bond breaking there. Okay. So if you like, what we're getting is a 1,2 shift of a propyl group in conjunction with the elimination of bromine. This 1,2 shift seems to be facilitated by the loss. It's almost like a backside attack on nitrogen to kick up bromine, like a nucleophilic substitution, except it's happening on this unstable intermediate that's formed. Well, by the way, this R group that I have up here obviously is bromine. Okay, so watch that. So when we're done, what has happened? Well, obviously we've kicked out another bromide. Our R group, I'm going to use R, is our propyl. It's now attached to a nitrogen, which has a double bond to a C, which has a double bond O. So this R group is our propyl. Okay. And we've produced isocyanate functional group. Well, having an isocyanate, we've now kicked out two bromides, so we've got our two bromides. We've got our two bromides. And we still have a ways to go to get this amine. We have moved, if you like, one of the carbons to the end of the molecule. Let's draw it again. So what have we gotten to? We've gotten to CH3, CH2, CH2, N, double bond C, double bond O. We've put the N in between the carbon, so we're very close to our propyl N. We have to get rid of the C double bond O somehow. How does that occur? Well, what happens is step 4. And that is hydrolysis of the isocyanate in base. What happens is hydroxide attacks. Hydroxide's a powerful nucleophile, and it attacks the carbon. You have 2 electronegative atoms attached to the carbon, oxygen and nitrogen. We move a set of pi electrons out onto the nitrogen, and we produce CH3, CH2, CH2, let you see the lone pairs. And now there's a negative charge on nitrogen. Of course, nitrogen's extremely basic. Water can come in and lose a proton. It goes off as OH minus, and we get the anion protonated back to the neutral molecule. Now, yes, we have an acidic hydrogen in the CO2H group that could be deprotonated, and certainly there's an equilibrium with the deprotonated form. But there are so many electronegative atoms attached to carbon in this case, with the nitrogen and 2 oxygens, that hydroxide can also nucleophilically attack the C double carbon here attached to the double bonded oxygen. And if hydroxide does attack there, we will produce we now have an OH, OH, O minus. Of course, we see we're set up with several leaving groups. We could reform the pi bond, kicking out hydroxide, but we also could kick out the amide here. If we do that, we reform the pi bond. And we get CH3, CH2, CH2, NH, two lone pairs, negative charge. And we have then H, O, C double bond O, OH. And this molecule that we formed is simply carbonic acid. Now, carbonic acid is a fairly weak acid, but it's still quite acidic. And in the presence of a powerful base, deprotonated amine is an amide. The amide's going to grab the protons. Also in hydroxide, which will fully deprotonate the carbonic acid. So that by the time we're done, all of the base that we've used will have generated the amine and the deprotonated carbonic acid becomes the carbonate anion, which is CO3, 2 minus. Okay. And so at the end of this reaction, after step 4, we have produced an amine that has one less carbon in it than the original amide. The last step, hydrolysis of isocyanate, has quite a few steps involved in the process. The most crucial thing, of course, was the 1,2 shift of the propyl group, the rearrangement to generate this isocyanate. Okay, well, we've covered a lot of preparation of amine reactions, so let's summarize. Now, based on your chemical knowledge, you could take an alcohol and convert this alcohol to several possible different amines. Either an amine that has one less carbon than the starting material, or an amine that has one additional carbon than the starting alcohol, or an amine that has the same number of carbons. For example, primary alcohols are readily oxidized to carboxylic acids. You can use any strong oxidizing agent that will produce an R, C, double bond O, OH. Reaction with SOCl2, thionyl chloride, will produce acid chloride. And if you hit that with ammonia, you can produce an unsubstituted amide, R, C double bond O, NH2. And we have just learned that if you hit unsubstituted amides with bromine and hydroxide, you can undergo a rearrangement in which you kick out the C double bond O as carbonate and you produce RNH2, in which you now have an amine that has one less carbon than the original alcohol. And so all the chemistry you've learned can be put into a series of steps that allow you to synthesize an amine. Of course, you could use SOCl2 or PCl3 or PBr3. Let's just call it PX3 as an example. And brominate the alcohol or chlorinate the alcohol directly. And put a halogen on in place of the alcohol. Primary halogens undergo nucleophilic substitution reactions, and if you use a powerful nucleophile like cyanide, Cn-, you can get SN2 attack. Nucleophilic substitution, SN2, will produce a C triple bond N, giving you a nitrile. Now if we reduce the nitrile using lithium aluminum hydride or catalytic hydrogenation, some reduction process, square brackets H means reduce. Lo and behold, we now have a RCH2, another CH2, and an H2. And you'll notice we've produced an amine with one more carbon, one extra carbon here. An extra carbon, one more than the original alcohol. Lastly, though, we learned that primary alkyl halides can be attacked by the phthalimide anion in what is called the Gabriel phthalimide synthesis. Gabriel phthalimide synthesis of a primary amine. Now, this Gabriel phthalimide synthesis involves nucleophilic attack SN2 and then subsequent hydrolysis of the phthalimide, and you will produce an amine with the same number of carbons as the original alkyl halide. So we have the same number of carbons as our original alcohol. So there you have it. At this point, you've learned enough preparation of amines and enough reactions of various functional groups to be able to synthesize an amine that has one less carbon, one more carbon, or the same number of carbons as an original starting material alcohol. Okay. What we want to do next is we want to begin looking at some of the reactivity of amines. And as in the case of carboxylic acids, when we focus on carboxylic acids and we first look at the reactivity of carboxylic acids, we focused on the feature of acidity, because acidity was a prominent feature of the reactivity of that functional group. Well, in the case of amines, a prominent feature of its reactivity is its basicity. And so one of the things we want to do is examine the basicity of amines. So we're going to look at the reactions of amines. And we're going to start by examining amine basicity. And so if we take a close look at amines, because nitrogen's somewhat less electronegative than oxygen, the lone pair it bears is more susceptible to protonation, and as a result, amines are more basic than corresponding alcohols. So that if we take a trivalent nitrogen, R3N, react it with water, an equilibrium will establish to produce R3NH plus OH minus. And the lone pair of the amine gets protonated. Now, any factor that makes the electron lone pair on the nitrogen of the amine more available towards protonation will increase the basicity. Any factor that makes this lone pair less available towards protonation will decrease the basicity. So let's begin looking at factors that will influence the basicity of amines. One of the predominant factors is inductive effects, including under this section we're going to look at both electron donation, electron releasing inductive effects, and electron withdrawing effects caused by electronegative groups. Suppose I examine or compare two amines, ammonia versus propylamine. If I react ammonia with water, I'll be in equilibrium with NH4 plus and OH minus. If I react this amine with water, I will produce the propanaminium ion actually let's make a bond there. Okay. Now, what is the difference in basicity in these two bases, ammonia versus propylamine? Well, ammonia has hydrogen in place of the carbon. Carbon is larger, more polarizable, has more electrons, and being non-electronegative, or of very low electronegativity, it tends to be electron releasing. That is, carbon pushes more electrons into the nitrogen through its sigma bonds than a hydrogen can. The net result of this is nitrogen, being somewhat electronegative, derives most of its electron density from this carbon, meaning it has to pull back on the lone pair to a lesser extent. It's obtaining more of the electrons it needs from the carbon. The electron donating effect or releasing effect from the propyl group makes the lone pair more available. Being more available means it protonates easy. If you look at it in terms of the resultant product, the alkyl group donates electrons that help stabilize the resultant cation. And the net result of this is that being more stable, it forms more readily. All right. So electron releasing effects can increase basicity. If a group is placed on nitrogen that donates electrons, the basicity of the amine increases. However, suppose I put an electron withdrawing group, like a fluorine, or chlorine, or something that withdraws electrons. Now the situation changes. Fluorine withdraws electrons from the carbon, producing a delta plus. This produces a smaller delta plus on the neighboring carbon, causing the carbon to withdraw electrons. If you like, electronegative nitrogen is able to pull less electron density from the carbon than it normally would. The net result is nitrogen pulls harder on its lone pair, making it less available for protonation. Electronegative groups cause an opposite effect. If you look at it in terms of the cation, withdrawing electron density results in more positive charge in nitrogen. Less dispersing of the charge results in disfavoring the formation of the cation because it is less stable. Now this can be readily seen if you look at some examples, such as several substituted anilines. For example, if we take para-nitroaniline and compare that to aniline, and compare that to para-toluidine, which is paramethyl-aniline, if we compare these three molecules and put down the pKb's, you see our trend in electronegativity is followed quite well. pKb of para-nitroaniline is 13.0. And by the way, you do not need to know these pKb's. Aniline has a pKb of about 9.37, and toluidine has a pKb of around 8.9. Lower number means more basic, so the toluidine is more basic than the aniline, and the nitroaniline is less basic. Why? Well, obviously, aniline donates electron density inductively, dumps electrons into the ring. Inductively doing so will cause the ring to be able to donate more electrons into the NH2. Nitro, on the other hand, has three electronegative atoms: electronegative nitrogen, electronegative oxygen. It's electron withdrawing. Withdrawing electrons from the ring makes less electrons available in nitrogen, so he has to pull back on its lone pair more, effectively shrinking the lone pair, making it less available for protonation. If you utilize the same analogy on the protonated species, that you say, for example, NH3 plus would form in all three cases, you could say that the inductive electron donation of the methyl helps make more electron density available to the nitrogen through the ring so that the positive charge is stabilized. Electron withdrawing effects of the nitro group make less electron density available from the ring to stabilize the positive charge. What's interesting in this case, however, is that there is also resonance effects. And so let's redraw these structures, if we could. Okay, and let's start with the methyl. In the toluidine case. And in the toluidine case, with the methyl, I have NH2 with a lone pair. I can dump this lone pair in and move it around the ring. Once again, I can move the lone pair, and these pi electrons move out. And in this case, we can talk about the inductive effects of the methyl groups and how it influences the delocalization of the negative charge from the lone pair. For example, we know that methyl pushes electrons into the ring. And if we label our resonance contributors A, B, C, D, and E, if we look at structure C, inductive electron donation from the methyl group will push electrons towards a negative charge. This is unfavorable. In other words, the negative charge in position C is not stabilized at all by the presence of methyl. If anything, inductive electron donation will destabilize contributor C. Furthermore, structures B and D, which put negative charges on the ring, will be somewhat destabilized by the inductive electron donation of the methyl. That is, structures B and D will make greater contribution when there is no methyl there. If I get rid of the methyls in case of aniline. So structures B, C, and D are disfavored in terms of contribution to the resonance hybrid by the presence of the methyl and its inductive electron donation. What that means is the negative charge, or the lone pair, spends less time out on the ring and more time in positions A and E, where the lone pair is on the nitrogen, where it is available for protonation. So one could argue that inductive electron donation somewhat disfavors delocalization of electron density onto the ring in the resonance. Now, this is a minor argument. It's the same basic thing as we've been saying through simple inductive electron donation, that pushing electrons towards the nitrogen makes the lone pair more available for protonation. But this type of argument is very important for the nitro group. I can draw very similar resonance structures for the nitro. In fact, I can do that. I can replace this now with an NO2, and let's do that. So there's an NO2. Here's an NO2. For this structure, I'll show you what the structure of NO2 looks like. There you go. Okay. So what happens in the case of NO2? We can draw the same resonance structures. And if I look at these resonance structures, well, obviously structure C is stabilized by the presence of electronegative nitrogen and two electronegative oxygens, very electronegative functional group, will stabilize the negative charge in that position, increasing the contribution C makes to resonance hybrid, simply meaning that the lone pair spends more time in this position. The electronegativity of the NO2 group will also helps somewhat stabilize structures B and D, overall increasing the contribution these make to the resonance hybrid, which simply translates into the lone pair spending more time out in the ring. If the lone pair is on the ring, it's less available for protonation. But we can go even beyond this statement, because I can extend the resonance effect by drawing one more resonance contributor. Now, of course, I forgot to put my positives on my NH2. Sorry about that. All of the double bonded NH2 groups should have plus charges. So here we go. And I draw this structure, and we've got an extra resonance contribute, F, where the negative charge lone pair is removed from the nitrogen, delocalized out to these oxygens. So nitro doesn't just withdraw electrons by inductive effects. Lo and behold, we see it withdrawing it by resonance effects as well. It's electronegative because of resonance. Net result of this really stands out, that the lone pair is less available for protonation because it spends more time off of the nitrogen by resonance. Electronegativity effects and resonance effects contributing to the lower availability of the lone pair for protonation. So there you have a discussion of inductive effects. Now, we can see some very interesting trends if we try and apply these inductive effects. In all cases, sometimes it can get rather confusing. For example, if I compare dimethylamine to trimethylamine, I would assume that because of greater inductive electron donation, making the lone pair more available, trimethylamine should be the stronger base. However, if I test its basicity in aqueous solution, I find that trimethylamine is the weaker base. And this seems to fly in the face of what we just talked about. Well, the reason for this has to do with another factor that's important in stabilizing our protonated cation that forms. And remember, stabilizing this cation helps to determine how strong a base you are. The more stable you are, the stronger the base the deprotonated form is. So, why would dimethylamine be a stronger base? Obviously, its cation must be more stabilized. Stabilized by what? Well, it turns out in aqueous solution, water molecules, delta plus on hydrogen, delta minus on oxygen, can solvate or weakly interact with the cation. So solvation effects help stabilize. The thing is, we get a sphere of solvation around a molecule. Water molecules will form a sphere around the molecule. And this sphere will have some optimal distance. Water molecules will arrange themselves, and there is a distance at which water molecules will approach, which will most stabilize the cation. The problem is some molecules are so sterically hindered that water molecules can't approach as closely. And so the sphere is larger. The interaction's weaker. The plus is less stabilized. And this is the case for trimethylamine. When trimethylamine gets protonated, the extra methyl group increases the steric bulk around the positive on the nitrogen. Water can't make as close an approach. As a result of this, the sphere of hydration is further out, and the stabilization of the positive is weaker. The solvation stabilization in this case is greater than the inductive effects, and as a result, Dimethylamine is a stronger base. Its protonated species is more stabilized by the solvation effect. Now, if this is true, if inductive effects are still present, it's just there's another factor, solvation, that's causing the dimethylamine to be the stronger base. If we remove the solvation effect, we should be able to show that trimethylamine, when there's no solvation available, is actually the stronger base. This can be done in the gas phase. If you measure the pKb's under gas phase conditions, you find out trimethylamine is indeed the stronger base. Another factor that helps affect or does affect basicity is hybridization. The hybrid orbital that the lone pair finds itself in can affect basicity. Whether the lone pair is in an sp cubed orbital, or an sp squared orbital, or an sp orbital, can directly affect the basicity of the lone pair. Sp cubed orbitals are larger. More p character means more diffuse. If you think about it, a lone pair in an sp cubed orbital, because it's larger, reaches out further than a lone pair in an sp squared, which would reach out further than a lone pair in an sp. Now, having a smaller orbital is like being more electronegative. You're held tighter, closer to the nucleus. So sp orbitals look more electronegative than sp squared, and sp squared look like they're held more closely, so the atoms being more electronegative than sp cubed. More electronegative holds tightly onto the electrons, making it less available for protonation. So having a lone pair in a more diffuse orbital results in easier protonation. This effect can be readily seen in bases where you have the lone pair in an sp squared, such as in pyridine, versus the lone pair in a molecule pyridine. In pyridine, the nitrogen's sp cubed hybridized. In pyridine, so let's write this down, pyridine, the molecule's lone pairs in an sp squared orbital because nitrogen's sp squared hybridized. The net result is pyridine's a much stronger base. In fact, if you check the pKb's, the pKb of pyridine's around 8.75. Again, you do not have to know these numbers, but you should be able to use them if they're given to you. The pKb for pyridine is 2.88. A lower pKb, stronger base, significantly stronger base. So hybridization is very important in establishing or influencing basicity. The next effect, of course, and we've somewhat seen how resonance can affect basicity already, is resonance. And resonance in the case of aniline versus the basicity of cyclohexylamine. Now, you've already saw me draw the resonance structures for toluidine. I'm not going to take the time to draw them again. The point is this lone pair can be delocalized around the ring. And so the lone pair being delocalized out onto the ring, is less available for protonation because it's partially resonance stabilized. Whereas in the case of cyclohexylamine has no resonance stabilization. Now note, the lone pair, if you do the hybrid orbital number count, right, is still sp cubed. But even this sp cubed orbital can have some side-to-side interaction with the aromatic ring, meaning the lone pair gets somewhat delocalized. That stabilizes the lone pair and makes it less available for protonation. How much? Well, if we look at the pKb difference between these molecules, pKb of aniline, of course, is 8.75. Ooh, I think that's a typo. Let me just check. We had the pKb. Yeah, aniline's 9.37. Sorry, 8.75 was pyridine's pKb. Okay, so if we look back at the problem we did, it was 9.37. And cyclohexanamine has a pKb of 3.3. Again, a significant difference. This time resonance, lowering the basicity. Let's look at pyridine again. Can pyridine? I said it was a hybridization difference. A pyridine has an aromatic ring. Is not the lone pair resonance stabilized into the aromatic ring? In actual fact, no. If we draw an edge-on view of our pyridine molecule and put in our 2p orbitals and link them up side to side to show our pi bond, pyridine is sp squared, and we have a pi bond here, we have a pi bond here, and we have a pi bond here. All of the 2p orbitals are involved in pi bonding. Where's the lone pair? The lone pair is perpendicular to those 2p orbitals. It's orthogonal. It's at right angles to the 2p's, and so it can't side-to-side overlap. It's localized in this orbital. It can't delocalize into the ring. Now let's look at an edge-on view of aniline and put in our 2p orbitals of the ring. Even if I draw the nitrogen sp cubed, so that I got an H here, an H here, and a lone pair here, I can imagine some side-to-side overlap with that lone pair into the ring. Now it is possible for the NH2 to rehybridize and spend some time in an sp squared state. It will be high energy, temporary, and put a lone pair in that sp squared state. If it does that, you see how the orbital can side-to-side overlap and delocalize with the orbitals in the ring. This can't be done in the case of pyridine. So in pyridine, it was purely a hybridization mode. But in the case of aniline, aniline has a resonance effect, which lowers its basicity, increasing its pKb value. Okay, let's try a couple examples, if we can, just a few examples, of the effect of basicity on amines and how we can utilize these ideas to explain the or assign which molecule is the stronger base. So I'm going to draw two molecules, and I want you to predict, if you can, which is the stronger base. And I'll show you the logic we use. Now remember, when looking at this, use the categories that we've just covered. That is inductive effects, solvation effects, hybridization effects, and resonance effects, and see if there are any differences between these molecules. Okay, so we're going to compare diethylamine to this molecule, and it is called pyrrolidine. So diethylamine has a lone pair on nitrogen, and pyrrolidine has a lone pair. And these lone pairs are susceptible to protonation. As such, both molecules are bases. Who is a stronger base and why? What do you think? Have you picked one? I'll give you a moment. Just pick one in the top of your head and see if you can at least get an idea ahead of time of which one you would think would be the stronger base. All right, let's take our categories. Let's start with hybridization. What's the hybrid orbital number of nitrogen? Well, each nitrogen has 1, 2, 3 atoms attached to it in a lone pair. Hybrid orbital number 4, it's sp cubed. 1, 2, 3 atoms, sp cubed. Hybridization is the same. What about resonance? Resonance effects. Well, there are no pi bonds in the system, and there's no apparent resonance stabilization of the lone pair. Hence, that does not play a role here. Okay, inductive electron donation. Well, let's look for inductive groups. This molecule has 1 H and 2 carbons. Carbon's more inductively donating than hydrogen. This molecule has 2 carbons, 1 hydrogen. The carbon's inductively donating into the nitrogen. Apparently no difference in inductive effects. This leaves only one category of information for us to distinguish between them, and that is solvation effects. Is there a difference in how close water molecules will be able to close approach the cation? And stabilize it? Well, if you think about it, this has two carbon groups, 2 arms off of it, if you like, that are free to move around, sweeping water molecules away from the positive charge. In this case, the two carbon groups are tied back, pinned back, as if your arms were tied behind your back, and exposing the positive more because of bond angles, and are less able to sweep around, less free to move around, sweeping water molecules away. Net result of this, of course, is that this molecule will allow close approach of water molecules. The water molecules will help stabilize the positive charge more, favoring the pickup of the proton. Hence, this molecule should be the stronger base because of a closer approach of water molecules or due to solvation effects. Let's try 2 other molecules. Let's compare pyrazine to pyridine. Who will be the stronger base? Pyrazine or pyridine? Well, this is rather simple. The hybridization is the same. There's no resonance. Both have their ring structure exposing nitrogen, so solvation effects will probably be similar. The difference here is inductive effects. The difference is this atom. Here it's a carbon, which is electron donating. Here it is a nitrogen, which is electron withdrawing. Electron withdrawing groups cause the orbitals, if you like, that contain the lone pairs to shrink. They help pull on the electrons a little more and make the electrons less available for protonation. Whereas the inductive electron donation of the carbon pushes electrons into the nitrogen, making the lone pair more available. Pyrazine has an electronegative group and as a result is less basic. The more nitrogens you add, the more electronegative atoms you add, the lower the basicity. A common mistake students make is they simply think, oh, there's 2 lone pairs, that must make you a stronger base. It doesn't work that way. Okay, well, we've covered a lot in this scribblecast. We've looked at the second half of the preparation of amines and introduced basicity as the first stage of the reaction of amines. Next Scribblecast lecture, we'll continue looking at the reactivity. I'm Dr. Brian Lloyd. This is my Scribblecast lecture. I thank you for listening.